you a brief overview of the basic features of ePMV and explain just a little bit about the science of what you're doing with this embedded Python molecular viewer, what all the buttons are, what these files are that you're manipulating, a general introduction to molecular graphics viewing through the embedded Python molecular viewer ePMV for 3D Studio Max. So let's begin. You follow the installation pages, you're up and running, and you have a version of ePMV similar to what I have here. This happens to be version 0.585, and actually that might be behind a little bit. This was from the download installation version 0.5.438 or 437. The Alpha2 version from Friday, November 16th, 2012. To begin with, let's just hop right in, and I'm going to click this Fetch button. And what that's done, you saw the only thing that happened is this current selection updated. So if we scroll down here to ribbons and check that, and I'm just going to zoom in. And let's just make this the whole window so you can see. What happened here is we have a 4-digit code, 1CRN, and that refers to one of hundreds of thousands or tens of thousands of protein database files that exist on a server called the Protein Data Bank. Which is a public repository for files that are resolved atomic positions of molecules posted by scientists and peer-reviewed and approved by scientists. So what I've done here is I've just clicked on a thing called the Molecule of the Month, and this gives you a nice description of one new molecule that's exciting in the PDB every month. And you can see here we're looking at a description of, what is this, vitamin D receptor? Vitamin D receptor. And David Goodsell writes an article for the general public that explains some interesting information about why vitamin D receptor, that's this blue and purple object, and each one of these little lumps is an atom. Why that's important, why it's interesting, and a little bit of its physical characteristics. And we can see here that it's wrapping itself very tightly around this orange and red DNA strand. So let's get back to our file. So we are viewing the atomic coordinates of this file, and this ribbon structure is a little confusing, so let's come back to that in a second. But first, let's click the atoms representation. And what a PDB file contains is a bunch of X, Y, and Z Cartesian coordinates for all of the atoms in a file. So we're looking at carbons in gray, oxygens in red, nitrogens in blue, there's a sulfur in yellow. And so these are very useful to show the actual structure of what one of these molecules would look like. Experiments can be done based on that, and a lot of information can be deduced from that. If we uncheck, so I just turned on the atoms, and what that does is it builds a sphere representation with a radius of that sphere equivalent to the average limits of the electrons for that sphere. So the carbon atoms are roughly 1.4 angstroms, if I recall off the top of my head. In diameter or radius. I have to look that up. It's been a long time since I've studied basic chemistry. And we can modify that using 3D Studio Max, just modifying this slider here. You can see that the relative ratios, the oxygen is a little bit smaller than the carbon is maintained, and we're just effectively scaling the radiuses of the root sphere that defines these van der Waals radii for this sphere. And I'll set that back down to 1. I'm not going to turn sticks on yet because we have a little bit of a performance issue with the current version of this alpha version for 3D Studio Max, so we'll turn that on at the end. But another thing that's available is the ribbon model. And what we're looking at here is proteins. All these atoms are not just a random cluster of atoms. They're built as a chain, a linear chain. So your DNA gets transcribed into mRNA, and then another protein machine called a ribosome translates that into a string of proteins, and those proteins fold together. And the proteins all have the same backbone atoms, but they have different side chains sticking off of them, so different groups of atoms. So if we go back to atoms, let's try this. And if we change down at the bottom here to color per residue, we're going to see each one of these different unique amino acids. So you can see that this blue guy is a pretty long one compared to one of these beige guys here. You can see that the blue guy has a ring of atoms. This is a tryptophan, if I recall correctly, whereas this green guy has just a few atoms sticking out and some upside down Mickey Mouse ears here. There are 22 common amino acids, and they're all strung together, and again they have a common backbone on them. And if you run a string along that common backbone, you can follow the chain itself, and then molecular biologists use, or structural biologists use, a shorthand here. So some of these atoms in the string have arranged themselves into a particular conformation called an alpha helix. So instead of just having a white string and trying to recognize that there's kind of a telephone cord shape, they exaggerate that part of it that has the telephone cord shape with a different, wider extruded shape. And then over here we have a set of the string interacting with a different set of the string. These are called beta strands, and together they make a beta sheet. And that has arrowheads on the tip of it, describing the flow of the chain itself. So that gives you little information. I know this is a lot and it's confusing, and I'm a bit tired, so I'm butchering some of the terms here, just doing this casually off the top of my head, but hopefully that explains a bit about what this is, a ribbon model. And if you show this to a cell biologist, a molecular biologist, pretty much any biologist, anyone who's taken a biology class and at the college level in the last 20 or 30 years, they will recognize this as a protein structure. Now let's turn off the ribbon and turn on the beaded ribbon. So this is just a slightly fancier version of the ribbon, and in a few days, if you update your ePMV software, we have some options here, and these allow you to change all these colors, so you can really customize the ribbon structure, and you can change the pink color on the inside of the helix to a nice dark gray to give it some depth, and change the outer color to a nice pretty blue, and change the beta sheets to anything you want, and you can get rid of the little bead on the edge, or you can exaggerate that. You can change the shape of the arrowhead. You notice compared to the regular ribbon that we have a nice taper on the tail of these arrows, and they're fully customizable, so you can create some really cool shapes and make a unique ribbon structure, but still one that's recognizable as a ribbon and a protein to the biology community. Let's turn beaded ribbon off and click MS-M surface. What that stands for, Michel Sanner molecular surface. So what this does is it actually rolls an atom with a radius, a sphere, over all of those original atoms themselves. So you can see that the atoms fit perfectly onto the surface of this molecular surface. And that sphere with a radius of 1.4 can't fit, as it rolls across the surface, it can't fit too deep into these grooves. So this is sort of giving you an idea of what a single molecule, let's say a water molecule, something with a radius of 1.4, it's giving you an idea of how much of these atoms are actually accessible to all of the solvent molecules that are banging into the outside of it. Because, again, these are atoms, so if you imagine a water molecule at this scale, it would be about the size of my cursor here. It would just be an oxygen atom with two little hydrogens sticking off of it like Mickey Mouse ears. And this protein will be floating in a sea of those water molecules. But water at this level is not the wet fluid that we imagine it. It's actually large, big red oxygen molecules, just like the other oxygen molecules that are inside the protein itself. So let's turn off the atoms, and I'll just show you some adjustments that are available on molecular surface. In most versions, when you click molecular surface, it will automatically be color-coded using this atom CPK. So it will look very similar to the, that didn't stick. Yeah, it'll look very similar to the original atoms that you clicked in terms of the color. We've got gray carbons, red oxygens, blue nitrogens, and the yellow sulfur that you can't see because it's inaccessible to the water molecules or to the probe radius atom is deeply buried there. And we can modify this. So I just learned we have a little bug that if you drag this slider too far to the left, we forgot to set limits on it, so it will crash 3D Studio Max. So instead of that, I'm going to drag it just a little bit to show you that you can modify these things by hand. And then I'm going to go in by hand to safely set this down to 0.1. So what I've done is I've created a really small probe radius. So now a tiny atom rolling around on the surface of this would be able to access a lot of these molecules. But effectively what it's done is created a mesh that's very tight to the surfaces of the original atoms. So I can color that. And if you were to render this or put a nice Phong break angle on the mesh itself, you wouldn't be able to really distinguish it from the original mesh, and that can, or from the atoms. And for large molecules, that can be a more efficient way to show an atomic representation as a nice single watertight mesh instead of as a collection of spheres. You can also reduce the density of the triangles a little bit. So let's knock this down to 1 and see if that works. Yep. So we've most of the time you'll be seeing these from far away, depending what type of animation you're setting up. And I'm just going to do a different color representation here. So last color representation was showing the atom types. Again, the carbons, oxygens, nitrogens. Now I've chosen this atom DG, that stands for David Goodsell. He's a guy that invented this coloring scheme that represents highly charged atoms, positives and negatives in saturated reds and blues. Neutral atoms are in white, and polarized atoms are in these desaturated pinks and blues. So that provides a lot of information to the scientist about the charge distribution along the surface of this molecule. Let's turn that off and turn on coarse molecular surface. So what this does, if we go back to our atoms here, this is creating sort of a, you can think of it as a Gaussian blur, kind of an averaging of the surface. So the high peaks are knocked down and the deep valleys are brought up a little bit. a blurred shape, and then that shape is iso-contoured or iso-hulled. And this has the same features. You can slide around and adjust these parameters, so I can make a big shape that encapsulates all the atoms. I can tighten that shape up a little bit to make almost a molecular surface with it. And if you push these settings to extreme, you can essentially replicate the molecular surface. But for the most part, you want to use this because if you have a lot of molecules on the screen at one time, as you would in the AutoPack software, another software that you can run by clicking this icon up here if you follow the installation tutorial, you can have thousands of these little molecules in one scene on the screen at a time, and you want them to be as simple as possible, because otherwise, if you render that, it just looks like a big scribble. You can't discern one molecule from the next. But with these surfaces, all the same coloring schemes are available, so we can see where the residues would penetrate the surface. You can see that little yellow atom is still poking through, so the surface is colored with the area representing that yellow residue, because I chose to color per residue. And let's turn coarse mole circle. Let's actually explore some other color variations. To do that, I think it'll be most informative if we go back to the molecular surface. So it's pretty cool. You can click and turn these things on and off, and you get all the functionality that one would expect from a molecular viewer. And I'm just going to set this back to the standard 1.4. Click return, and let's get a little prettier triangle density here. Knock it back up to 3. And let's go through and update these colors. So again, we can see all the atom types. We can see the charge distribution on the molecule. You can sneak around, and I think you can see some of the sulfur on the back side. So here we've got, again, highly charged atoms versus polarized versus neutral in white, according to that David Goodsell coloring scheme. We can see the residues, and these are just different sort of canonical colors, one representing every residue in the molecule, and there's a different coloring scheme, but it's effectively doing the same thing. It's just a different color selected from a different underlying molecular graphics software package. We can color by secondary structure. Now, secondary structure is a term biologists use to describe those telephone cords versus the pointy arrows. So we have four types of secondary structure visible in this molecule right here. There are random coils in white. There are beta strands in yellow making up beta sheets. This molecule doesn't actually have a hairpin turn, but in some other ones we'll investigate in other tutorials, you'll see that parts of these random coils are blue, and that's a specific type of turn that has a specific set of angles for that little white rope relative to itself. And then we have alpha helices in pink here. And so these default coloring schemes are pink and yellow for our particular viewer here. And you can see that those, again, the atoms that are sticking out with their large side chains from this surface, from this backbone, are color-coded to match it. So if we turn MSMS back on, you see the pink region is pink, the white is white, the yellow is the yellow. Let's choose a different scheme. So chains. This isn't too meaningful in this particular scene, and I'll show you a different scene a little bit later or in a separate tutorial. this molecule only has one chain, so it's one continuous string of amino acids going from a starting point to an ending point. There are a lot of proteins or molecules where a second one of these will stick together with this one, forming a dimeric interaction, meaning that two objects are stuck together, or a trimeric if three objects are stuck together. And this is called quaternary structure, when the secondary structure I told you about, the helices and the strands, are folding together into this large 3D structure. That's called tertiary structure, and if two or more of those stick together, that's called quaternary structure. Anyway, if you choose to color by chain each one of these blobby shapes, each one of these molecules in the multimeric protein will have a unique color associated with it, no matter what representation you choose. Currently we have a bug where the ribbon models are not being updated by the coloring scheme, but again, if you look at the top here, we ask you to update this alpha version regularly, and you do that by going to Help, check for Update, and a little thing will pop up if there's a new version available, and you click OK, and you can automatically update without having to go and install a new version. So a lot of these functions are dimmed out right now for this very early alpha version of ePMV, and if you continue to update on a regular basis, you'll see each one of these features being added back every day. Okay, that was pretty rough and long-winded overview of the basics of molecular graphics viewing inside of 3D Studio Max using the brand new embedded Python molecular viewer and the SciViz plugin from Autodesk. And I want to thank Ludovic Altine and Christopher Diggins for the hard work they've done to make this available. And I'll do a more thorough and more exciting tutorial as this develops in the coming week. So please stay tuned, come back often, download, install, and update often, and we'll show you some of the cool features very soon where you can, for example, load this WDNA server and just type in a sequence, a DNA sequence, and it will automatically build a DNA strand into your scene. If you check out some of the tutorials, it shows you how to build a poliovirus from scratch using the proper coordinate files. And the beauty of this system is that you're automatically building these molecules using proper scientific coordinates and getting very accurate files with almost no work. And so you can concentrate on lighting the scene, setting up the animation, and doing accurate, engaging work with these really interesting, unique shapes with the most efficient method possible. Thanks very much.